All right, welcome back, everyone. So now we're going to fill in these two boxes with some more derivative formulas. And some of these we've already seen, and some of them we aren't going to derive together, but you can use the same techniques that you saw in example 1 and 2 of this section to derive them on your own. All right, let's get started filling in here. So derivative of ln of x, we saw this in the first video, is 1 over x. Derivative of arcsine, we saw in the second video, example 2, is 1 over square root of 1 minus x squared. And then now we have derivative of log base a of x. We don't see this one too much, but the derivative is 1 over x ln of a. And here, a is a constant. So a doesn't change. If a is equal to the constant e, then we have the same ln function. So just to recall, that's where natural log comes from, and that's what we see here. Okay, and then we have derivative arctangent. Again, we won't derive this together, but you can look online if you want to see an example, or you can use the same techniques that we've been using with inverse functions to derive it. And the formula looks like 1 over 1 plus x squared. All right, so now we just have to finish out these derivative formulas, some derivatives involving exponents. And actually, you've seen some of these before in the first sections of our chapter when we started looking at formulas for common derivatives. So here in all of these, a is a constant. So this first function, the constant is in the power and the base is the variable. So we've seen this before. This is called the power rule. And that is the derivative is a, so the power comes down, x to the power of a minus 1. And then now let's look at this other function, a to the power of x. How is this function different? Well, here the base is a constant a, and the power is our variable. So the power varies here rather than the base. So that derivative, you can compute it using the same method in this class, because we can use that, the ln, or rather the log, base a of x undoes the exponential. So what that looks like, log base a of a to the x is equal to x. So this is going to be your starting formula that you take the derivative of both sides and play around with that. When you do that, you get that the derivative is a to the x times the natural log of a. All right, and then the last type of function that we see is when both the base and the power are themselves a function. So notice this is different than a chain rule because we don't have a composition of functions, but we have a power inside, or a function inside the power, and a function in the base. So here I'm just going to say there's a special technique that we won't see too much in this class. So there's no formula for this because it depends on the functions that we're using. But I do just want to make a note of that special technique so that you're not left to wonder, and you can, your curiosity can be a little satisfied here. So the technique is to take the ln of both sides. So just to give you a taste of what that looks like. So if we start with y equals f of x to the g of x, then if we take natural log of both sides, let me get some color coding here. So natural log. So we have y f of x to the g of x. Now that right-hand side, based on properties of exponents, that g of x comes down. So this just becomes g of x times ln of f of x. And so now from here, ln of y and g times ln of f, now we take derivative of both sides. So take ln of both sides, take derivative with respect to x of both sides. And what ends up happening is that you're able to compute that derivative, or the derivative of y, because that will come out when you compute the derivative of ln of y. Okay, so it's pretty cool. Just wanted to show you that, but don't worry, you won't have to do many of those problems on your own. And I'm more than happy to work out more examples for you. All right, so please pause, rewatch the video, make sure you have these boxes filled in. And then when you're feeling ready, please continue on to the next video.